we would like to find the image of the ray, theta equals 7 pi over 4, under the map W equals the principal branch of the logarithm. So let's look at this ray here, theta being a polar angle, 7 pi over 4. So 8 pi over 4 would be 2 pi, which would be a full revolution. So we want to be pi over 4 short of that. So it's here. So this is the angle. Theta equals 7 pi over 4. And for the sake of argument, the ray here should not include the origin. We can't take the log of 0. 0 is not in the domain. So this ray has positive radius associated with it. So r is bigger than 0. So this is the line here. This ray is on the line y equals negative x, the 45-degree line below the x-axis. Okay, so that's our domain, this ray here. Let's emphasize it in red, because there's a lot of other stuff there. So that's the ray, that's our domain. Okay, so what's the image of that? So W, which is equal to U plus IV, is equal to the principal branch of the log of Z, which is defined as the natural log of the modulus of Z plus I times the principal argument of Z. So this is the principal argument. In general, the argument of a complex number consists of infinitely many angles. When you write the capital A here, that's the principal argument, and that selects one of the angles. The principal argument is the angle between minus pi, and it could include pi. So for every number in the complex plane except 0, there is exactly one angle in this interval associated with the position of that point in the complex plane. Okay, so it looks like U, the real part, is equal to the natural log of the modulus of Z, and V, the imaginary part, is equal to the arg of Z. So on this ray here, the argument, one argument of Z is 7 pi over 4, but that argument is not in this interval. So we have to observe that 7 pi over 4 and 7 pi over 4 minus 2 pi, these are coterminal angles. And so either one of them could be used to represent an argument. And the second one here is in the proper interval, because 7 pi over 4 minus 8 pi over 4 is negative pi over 4, which is between negative pi and pi. So V is equal to negative pi over 4. So V is a constant, and U is log of modulus of Z. Now the modulus of Z is going to go anywhere from 0, not including 0, to infinity. So the modulus of Z will go from 0 to infinity, which means that the log is going to go from minus infinity to infinity, because the log function has as its domain, the ordinary real log function has as its domain 0 to infinity, and as its range minus infinity to plus infinity. So U is going to go between negative infinity and infinity, and V is negative pi over 4. So in the Z plane, our domain again is this ray here, with this angle being 7 pi over 4, And then the mapping W equals the principal branch of log Z is going to give us a horizontal line where V is the constant negative pi over 4, so this is the number negative pi over 4I, and U is anywhere, this is the U axis, U is anywhere from negative infinity to infinity, and there's IV, so let's just touch that up. Let's put this a little bit below it. So this is the image, this line here, and this value is negative pi over 4 times I. So this is our domain, and this is our range. Let's look into this a little bit more deeply. I'm wondering which point on the ray actually maps to this imaginary number here, this purely imaginary number, negative pi over 4I. So we'll notice that, again, as mentioned at the top, this ray is on the line y equals negative x. So a point on it has the form a, or some positive number a here, and then minus ai. This would be minus ai. So that's what a point looks like. So which point maps to this one? So we want to take the principal logarithm of such a point and see what a has to be in order to make the output exactly this. So the principal logarithm is the natural log of the modulus of a minus ai, and then plus I times the arg of a minus ai. Now, the modulus of this complex number is the square root of a squared plus a squared, so the square root of 2a squared. And the argument is minus pi over 4. So we're going to get the correct imaginary part, of course. And now we want the real part to be, here u is equal to 0. This is 0 on the u axis. So we would like the natural log of, this is just a real number now, 2a squared to equal 0. And of course the log of 1 is equal to 0. So we would like the square root of 2a squared to equal 1 to make this logarithm equal to 0. And that means 2a squared is equal to 1. And that means a squared is equal to a half. And so algebraically, a is plus or minus the square root of a half. But in our situation, based on the fact that the ray is in the fourth quadrant, a is positive. So a is the square root of a half, which is 1 over the square root of 2, or the square root of 2 over 2. So that would be the point right there. That point is right there is root 2 over 2 minus root 2 over 2I. That's this point here. I'll put it in red. And that maps to this point. Now, as the z moves in this direction along the ray, away from the origin, the modulus of z gets larger, and that means that u gets larger. So as we move this way on the ray, we're going to map to larger values of u. So this part of the ray maps to this half of the line. Meanwhile, as z moves towards the origin, the modulus of z moves towards 0, and the log of z will move towards minus infinity. So that means u will move towards minus infinity, which is this way. So a little bit more detail here. This portion of the ray, that finite portion of the ray, maps to this infinite line, this is a ray here in green, and this infinite part of the ray maps to the other half of the line, this also infinite ray over here. So there's a little more detailed look at how this ray maps onto this horizontal line.